Okay, so this will be another lecture over spectroscopy. So in this case, we're going to cover what's known as cover the very basics of carbon-13 NMR spectroscopy, or C13 NMR. So the basic theory is for carbon-13 NMR is the same as for proton NMR. So carbon-13 is NMR active, so that basically means that that nucleus has nuclear spin. So same basic theory as proton NMR. So the carbon-13 could be spinning like that, in which case it has a magnetic field in that direction, or it could be spinning counterclockwise, so it has a magnetic field in that direction. And if you put that in the presence of an external magnetic field, then those two nuclear spin states become unequal in energy. So one difference between carbon-13 and proton NMR, though, is that energy difference between the spin states is only about a quarter of that for carbon-13 than it is for hydrogen for proton. So if a proton needs to do spin flip, it needs 200 megahertz radio frequency radiation. To do spin flip, the carbon-13 nucleus only needs 50 megahertz. Okay, so the main isotope of carbon is carbon-12. So 6 protons and 6 neutrons in its nucleus, and that's about 98.8% natural abundance. But that carbon-12 nucleus does not have spin, so it's not NMR active. Carbon-13, which has 6 protons and 7 neutrons, does have nuclear spin, so it's the one that's NMR active, but its natural abundance is only 1.1%. So in contrast, the proton, its natural abundance is 99.9%. So if you had a molecule, the chances of there being H1s in the molecule is highly likely, right? Because it's 99.9% natural abundance. The chances of there being a carbon-13 in that molecule is minimal because there's only 1.1% natural abundance. It's much more likely that you would have a molecule with proton H1 in it and a carbon-12 nucleus, but that is not NMR active. So this will be one downside to carbon-13 compared to proton. Because there's only 1.1% natural abundance, you get much weaker signals out of carbon-13. Furthermore, the carbon nucleus is about 1.6% as sensitive as the proton is. So you put the two together, you put the natural abundance and the fact that the nuclei of carbon are just not as sensitive to begin with, then that means basically what you end up with is that carbon-13 NMR, so carbon is about 1/5700th less sensitive or as sensitive compared to proton. So there's consequences to this. So the consequences, a couple of consequences. So one, that means you either need more sample because there's not very many carbon-13s in molecules because it's only 1.1% natural abundance and they're not very sensitive. So that means you need more sample so that you can make a more concentrated sample, right? If the sample is more concentrated, then there's going to be more carbon-13 nuclei present. Or the other thing that you would have to do to compensate for this is that you have to do more scans. So typically what's done in NMR is you scan the sample multiple times and then you take the average of all of those scans. So that'll minimize noise in the spectra and that'll enhance your signal in the spectra. So for proton NMR, you typically only need to scan your sample about 8 to 128 times is what most people do. And so that can just take seconds to, if you only did 8 scans, that can be done in a few seconds, or 128 scans a few minutes, right? But for carbon-13, since it's less sensitive and there's less carbon-13 nuclei present, if you can't make a really concentrated sample, then you have to do a lot of scans instead. So you may scan your sample 1,000 times or 20,000 times or 100,000 times and take the average of all of that data. So carbon-13 then, if you have a really concentrated sample, then you could just do maybe 1,000 scans or less. You could do that in an hour. But if you don't have enough sample to make a really concentrated sample, then you have to go to 20,000, 100,000 scans or more, and then that can take 1 or 2 days to do that experiment. Okay, so just like proton NMR, there are characteristic regions. There are characteristic regions in carbon-13 NMR as well. So the scale's a little bit bigger. So carbon-13 NMR is typically from about 0 ppm to about 220 ppm is where you see your signals at. So if you see a signal between 180 and about 220, so if there's a peak in there, then that is typically the carbon of a carbon-oxygen double bond. Right, so if you see a peak at 190 ppm in carbon-13 NMR, you have a C double bond O in the molecule. So that means it's an aldehyde or a ketone or a carboxylic acid or an ester or an acid chloride or an anhydride, right? Some molecule that's got a C double bond O in it. If you see a peak between about 140 and 180, that is typically carbons in an aromatic ring like benzene. And 100 to 140, then that would typically be carbons in an alkene. And that's really about it. That's the main characteristic regions for carbon NMR. I mean, if you have a carbon attached to a really electronegative atom like an alcohol, then this may be anywhere from about 50 to 80 ppm. But most other signals in carbon NMR are somewhere between 0 and 100 ppm. But these characteristics regions are nice because it's easy to pick out if you have an alkene or an aromatic part of your molecule or a C double bond O. And so you typically, since most of the time you're doing NMR as a solvent in chloroform, CDCl3 has a signal at 77 ppm. It's a pretty complex signal, so you see a lot of peaks there at 77 ppm. That's just your solvent, and you can ignore that signal. But you do have to look close around it to make sure there's not an extra signal around there that may be coming from your sample. Okay, so there are different types or different ways to do carbon-13 NMR. We'll look at 4 different ways. So you could do what's called coupled carbon-13 NMR, but this is not very commonly done because it gives very complex spectra. And we'll explain why in just a minute. So basically, that type of carbon-13 NMR, carbon splits with all hydrogens within 3 bonds of it. So that's how you count the neighbors. Any hydrogens within 3 bonds is a neighbor, and then +1 in +1 rule, that's how many peaks you would see for the carbon signal. Or you could do what's called off-resonance decoupled. In this case, carbon only sees the hydrogens directly attached to it. So you get what's called 1-bond coupling. And I'll go through this in just a minute to make sure it makes sense. Or you can do what's called broadband decoupled. That's the most common, but you lose some information, as we'll see. In this case, all carbons are singlets. So carbons are not split by any hydrogen in the molecule. Or you can do what's called depth. And so those would be the main 4 that we look at. For a graduate course, we'll look at some other examples of carbon-13 NMR experiments that can be done. Okay, so let's go through these 4 different ones. So if you did a coupled carbon-13 NMR, so carbon can split with all hydrogens within 3 bonds of it. So if we take this first carbon, for example, that's 1 bond, 1 bond, 1 bond, so it can split with all 3 of those hydrogens. Or that would be 1 bond, and then these would be 2 bonds away, so it can split with those 2 hydrogens, and that's 2 bonds away. Or those are 3 bonds away, so it can split with those hydrogens as well. So that 1 carbon would have 1, 2, 3, 4, 5, 6, 7 neighbors. 7 plus 1 equals 8 peaks. So that would be an octet. And if we go to the next carbon, so if we go to that one, so that would be 1, 2, 2, 2. So those are the CH3s within 2 bonds. This would be 1 and 1, so those 2 are going to split it. This will be 1, 2, and 2. So the CH2 is within 3 bonds, so that's going to split it. That's 2, that's 3, so that CH is also within 3 bonds. So every single hydrogen in the molecule is within 3 bonds of that carbon. So it would split with every single one. So that's 1, 2, 3, 4, 5, 6, 7, 8 neighbors. 8 plus 1 equals 9 peaks. So for this one, 1, 2, every single hydrogen is within 3 bonds, so that would be 9 peaks. And for this hydrogen, so 1, 2, 3, that would be a triplet. Only the CH2, 1, 2, is within 3 bonds. So the splitting is very complex, but furthermore, these are very similar in chemical shift. And because coupling constants are absolutely huge in carbon-13 NMR between carbon and hydrogen, these two signals would overlap. Probably all 3 of these would overlap. And you would just have a mess of a spectra that's very difficult to interpret. Okay, so this one would be easy to interpret because that carbon is way downfilled at about 180 to 220 ppm, so that signal would be well resolved, but the other 3 signals would be just overlapping each other, and it'd be just a complex mess to interpret. So usually that's not done. Or you could do what's called off-resonance decoupled. So in this case, you only have 1 bond coupling, so carbon only sees the hydrogens directly attached to it. So if we take this first carbon, for example, that's 1 bond, 1 bond, 1 bond, so that carbon only sees 3 neighbors, so it'd be a quartet. And this carbon, that's within the C, so the 2 hydrogens directly attached to it are within 1 bond, so that would be a triplet. And same here, that would be a triplet. And this one, that's the only hydrogen within 1 bond, so it would be a doublet. So basically off resonance decoupled, so all CH3s are quartets, all CH2s are triplets, all CHs are doublets, and all carbons with no hydrogens are singlets. So since you reduce the number of peaks, you reduce the number of possibility of overlap, but still, because the coupling constants are so large, you would probably still see that these 2 signals would probably overlap each other. And so then it becomes difficult to interpret. So what's usually done then is just to do what's called a decoupled carbon-13 NMR. So when you do this, you keep all of the hydrogens in the molecule in the excited state all of the time. So how do you do that? So you're basically constantly hitting the protons with radio frequency irradiation to make them do nuclear spin flips to keep them all in the excited state, aligned opposite of the magnetic field all of the time. So if this is your magnetic field, you're constantly sweeping the radio frequency so that hydrogens are always absorbing energy and always spin flipped against the magnet. So all of the hydrogens are aligned against the magnet all of the time. So now the carbons only see one environment around them. And so basically what this means is that all carbons become singlets. So that's a singlet, that's a singlet, that's a singlet, that's a singlet. So now there's minimal chance of signals overlapping since all carbons are singlets. And so you have it's easier to interpret your spectra. But you've lost some information, right? Because since that's a singlet, you no longer know how many hydrogens are attached to it. So you lose some information, but at least you can count your signals. Right, so the downside to this is there's no splitting, so you lose information. The upside is that there's less likely to have signal overlap, so you can just count the number of carbons in your molecule. Right, however many signals you see, that's how many carbons are in your molecule. Unless there's symmetry in your molecule and some carbons are the same, then you would have fewer signals than actual carbons in the molecule. So if we take an example, so if we took these 3 molecules, they're all C4H8, so they would all have the same mass. So unless you can interpret fragmentation patterns, mass spectrometry would not be a good way to differentiate between these 3 molecules. They all have aromatic rings and CHs, so they're all going to have very similar IR spectra. So unless you're an expert at IR spectra, it would be very difficult to distinguish between these 3 molecules using IR, but it would be trivial using carbon-13 because how many different signals would you see? So for this first molecule, there's a plane of symmetry there, right? So you have 1, so that's the same, 2 is the same as that, 3 is the same as that, and 4 is the same as that. So you would see 4 signals in carbon-13 NMR. And for this molecule, there's a plane of symmetry there. So that carbon's the same as that. That's the same as that. That carbon's unique. That's the same as that, and that carbon's unique. So this would have 5 signals in carbon-13 NMR. And in this molecule, there's a plane of symmetry here, and there's a plane of symmetry there. Right, so that carbon is the same as that. 2 methyls are the same. That carbon is the same as that. And then this carbon is the same as that carbon, which is the same as that carbon, which is the same as that carbon. So there's only 3 signals in carbon-13 NMR for that. So if you had 3 samples and you didn't know which was which, sit down and take a carbon-13 NMR, and you do 2 of the samples, and now you have all 3 of them figured out, right? Just count the number of signals that you see in carbon-13 NMR, assuming all of the carbon signals are resolved so that you can see them all. Of course, you could also do this faster by doing proton NMR, since you can do a proton NMR faster than a carbon-13. So if we did the same, how many signals would you see in proton NMR for each? So again, that would be the same as that. There's no hydrogens here, so you wouldn't see a signal there in proton NMR, but you would see one for that and that. So in proton NMR, you would see 3 signals. And for this, you would see that. There's no hydrogens here, so you don't see that, but you do see this hydrogen, you see that hydrogen, which is the same as that, and you see that hydrogen, so that would be 4 signals. And for this one, again, since there's 2 planes of symmetry, you would see the CH3, 1 signal, and then this is the same as this, which is the same as this, which is the same as this. So you would only see 2 signals, right, because there is no hydrogens on that carbon. So 2 signals, 3 signals, 4 signals, you could easily distinguish between those 3 isomers. 5 minutes of NMR experimentation. Okay, so let's do this. So let's sketch the carbon-13 NMR of this molecule. So one thing to note in carbon-13 is that integration does not work. So proton NMR, you integrate the signal, and that can tell you how many hydrogens are on each carbon. But carbon-13, that doesn't work, because in carbon-13, right, so you excite the carbon-13, it does a nuclear spin flip, and then they flip back and they give off energy, and you measure that energy that's given off. But the problem in carbon-13 is that all carbon do not relax at the same rate. Some react fast, some react slow, and so that messes your integration up. So you can't measure the area under a carbon signal and know how many carbons that's is giving rise to that signal. But usually what you find is that CH3 are usually the most intense signals, because the hydrogens attached to the carbons help the carbon once they excite, the hydrogens help them relax back to the ground state. So CH3s are usually the most intense signals, and then CH2s, and then CHs. And carbons without any hydrogens usually give weak signals. Since they have no hydrogens attached to them, they relax back. Once excited, they relax back to the ground state very slowly. Okay, so if we did the carbon-13 NMR of this molecule, how many different carbons are there? That carbon's the same as that, that's 1. And then that carbon's 2, that carbon's 3. These are the same, so that's 4. These are the same, that's 5, and then that one is 6. So 3, 4, 5, and 6 would be in this region, the aromatic region. And then 1 and 2 are alkanes, they would be in this region. So this would be what your carbon-13 NMR looks like if we assign the signals. This is carbon 1, this is carbon 2. And again, so there's 2 carbon 1s, so the signal is going to be a little bit bigger than the signal for carbon 2. And furthermore, they're CH3s, so they're going to typically be a little bit more intense. And then in terms of 4, 5, and 6, so the 2 smallest peaks will be the 2 carbons that have no hydrogens on them. So this would be carbon 3 probably, and carbon 6. And then carbon 4 and 5 they have hydrogens on them, so they're going to be a little bit bigger. Plus, there's two of them, giving rise 2 carbon 4s and 2 carbon 5s, so those signals are going to be a little bit stronger. And if you did the proton NMR for this molecule, so the 2 CH3s have 1 neighbor, so they would be doublet, right? So they're there. And that has 6 neighbors, so 7 peaks, so this would be number carbon 2. And then these hydrogens are all on the aromatic ring. So if you remember in proton NMR, they're going to be around 7 and 8 ppm. So you would have doublet, triplet, triplet, right? Because this hydrogen has 2 neighbors on 5, and this has 2 neighbors between 4 and 6, and this has 1 neighbor on carbon 5. So you would see, so this would be 4, the doublet, and the para would probably be upfilled, so that would be this triplet, and the meta would probably be more downfilled, so it would be that triplet. So one thing to notice between carbon 13 and proton NMR is the signal's pretty well aligned. It's not always the case, but usually the first signal in carbon 13 is going to correspond to the hydrogens, the first hydrogen signal in proton NMR, and you know that is the next signal in carbon 13, so the hydrogens on that carbon would typically be the next signal in proton NMR. So the signal's pretty well aligned between carbon and proton, but not always. Okay, so take these 2 molecules, how many different carbon signals would they have? And how many different proton signals? So there's a plane of symmetry here. So 1 would be the same as that, 2 would be the same as that, 3 would be the same as that, 4 would be the same as that, and 5 would be that carbon, and then this carbon is the same as that, that's the same as that, and then that carbon. So there would be 8 carbon signals in the molecule. And for proton NMR, you would have the CH3, you would have the CH2. There is no hydrogen on carbon 3, so you don't see a signal there. So you would see this signal, and then you would see this signal, and there is no hydrogen on carbon 8, so you would not see a signal there. So carbon 13, you would see 8 signals. Proton NMR, you would see 5 different signals. And of course, carbon 13, if you did off resonance, or if you did broadband decoupled, you would just see 8 separate singlets. For proton NMR, you would see a triplet, a quartet, a singlet. So this would be triplet, right? This would be quartet, this would be singlet, and this would be doublet, and this would be doublet. Okay, and in this molecule, so how many carbons would you see? So that's the same as that, and then that's unique, that's unique, that's unique, that's unique, that's unique, that's unique, and then this CH3s are all the same, so 8 carbons there. How many hydrogen proton signals would you see? You would see 1 there, you would see that, you would see that. There's not 1 at 4, so you would see that, you would see that. There's not 1 at 7, no hydrogen on 7, so you would only see 6 different signals in proton NMR. And of course, again, in carbon 13, if it's broadband decoupled, all of those 8 would just be singlets. And then in proton NMR, this would be doublet. This number 2 has 3, 6, 8, so that would be 9 signals. 3 has 1, so that would be doublet. 4 has 2, so that would be triplet. 5 has 2, 3 neighbors, so that would be quartet. And 6 has no neighbors, so that would be singlet, right? Which one would be farthest downfield in carbon 13? So let's circle the one that's farthest downfield in carbon 13. It would be that, right? C double bond O would be about 180 to 220. And proton NMR, which would be the farthest downfield, would be that, since it's next to oxygen. And the electronegativity is going to affect the chemical shift there. Okay, and then lastly for carbon 13, we'll just briefly mention this experiment known as DEPT. So there are different depth experiments that you can do. You can do what's called a depth 90 and a depth 135. So we're just mainly going to look at how to interpret the signals from those type of experiments. So first of all, you would do a broadband decoupled. So all carbons are singlets. So that's what this is trying to represent: singlet, 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 singlet. And then you would do a depth 90 experiment. So all carbons with no hydrogens, the signal would disappear, so no signal. All CHs, the signal would still be there, so you'd still have a singlet for that carbon. All CH2s would disappear, those signals would disappear, and all CH3s would disappear. Okay, so right away you just do 2 experiments, a broadband decoupled and a depth 90, and now you know all of the CHs in the molecule, because all of the CHs are the only one that would give a signal in both experiments. And then you do a depth 135, and for the carbons with no hydrogens, they're still gone. So now you figured out all of the carbons that don't have hydrogens, because they're the only ones that have a signal in broadband decoupled, but depth 90 and depth 135, the signal disappears. So any signal that disappears both in depth 90 and depth 135 is a carbon with no hydrogen on it. So CHs are still there. So now you've got your CHs figured out, because the CH3s are both present in a depth 135, but they're not both present in a depth 90. And then CH2s are easy to pick out because they turn upside down. Their signals are upside down in a depth 135. So you do a broadband decoupled, and then you do a depth 135, and any signal that's upside down is a CH2. So basically what this allows you to do is it allows you to get information back, right? So you do the decoupled, you lost information because everything's a singlet, but then you do the depth and you get that information back in terms of how many hydrogens are on each carbon. You still don't know how many hydrogens are on adjacent carbons, but you at least now know what's a CH3, what's a CH2, what's a CH, and what's a carbon with no hydrogens on it. Okay, so that's the basics of carbon 13 NMR.